Welcome to a new test and teardown video. This time we're going to play a little bit with an immersion switch mode power supply. The model is called R48 2000E. Yes, it is a 2000 watt output power supply and it weighs only a few kilos. It is actually quite small and very, look at that. And here you go. The input is from 100 to 250 volts. And 13 amp, that is at 250, by the way. So yes, 2000 watts of output. And you may think that this is a regulated 48 volt output. That is not really true. This is a 48 volt lead acid system battery charger power supply. So it's a very, very special power supply, and it will give you about 55 volts no load. So you can't really use it for 48 volts stabilized before you do some modifications and stuff like that. And it is specially made for GSM cell phone setups. I pulled this out from a rack. I got 3 of these, and the rack could contain 5 of them in parallel. So they are parallelable and hot-plugable. And this is why you have these really nice plug-in connectors like that. So this is mains input, and this was of course in the rack, and this was the 48 volt rail power connector. As you can imagine, it was mounted with some big copper bars all the way through, because the resulting total was about, I think, 200 amps or something like that when all of these they were populated. So yes, of course you need some real solid copper bars, and that is why this connector is designed like this. You can see copper bars on the top and the bottom. Quite smart. This little connector here is for RS 485 or something like that, I think so. I got this cable system here for all the different power supplies, and they were just in parallel. And in each end of this wire system, we got a termination resistor. So I believe this is some serial communication that will tell the main controller supervisor that this and this power supply is not working, and then you need to replace it. And you can do that while the whole system is still running. So how about we plug this in and see how well it works. And by the way, they are inrush current protected, and you can start these with a tiny little fuse on your mains and all that, because of course they're hot pluggable. So the input rectifier system here is specially made not to pull any nasty inrush current. That is something I really like. So let's try and power this one up. I got a voltmeter on it. See? No nasty clickety. And it's using 37 watts in idle. And of course we got the green. Oh, that is really weak. We should have a green on LED. So 36 watt it is now, the idle power. I just found the specifications and all that kind of stuff online, and it says 97% efficiency at full power. That's quite amazing. Let's look inside this wonderful power supply. Yeah, half of it is air. Less than half, right? And that is probably the big hefty output transformer. That will be an inductor for something related to the primary side, I guess. And I think those two inductors, that will be power factor correction. So we probably got two sets of transistors. I can only see, if I look really, really careful down here, I can see two transistors. So that's involving the primary side, and then I can see two more transistors up there. I don't know if you can see them right now. I think that's related to the primary side, so it's maybe only a half bridge push-pull, or maybe it's a full bridge. I don't know yet, because I don't know if there's any hidden transistors on the other side of that little heatsink there. There's one very, very disturbing finding, and that will be the 4 field effect transistors that you can see right there. I think this is the synchronous rectifier for the output, and that explains, of course, the very, very high efficiency. But they're not mounted, like they're not screwed to this aluminium. So this piece of isolation kind of material we see here, it doesn't really feel like it's sticky. So why do they stay there? I don't understand this. How is this done? This can't be good. It looks like something is missing here. There's normally a piece of metal and some screws and some stuff like that. So that troubles me a little bit. Also, I've been trying to see if I can find the primary side. This is input, right? So this is the primary side input. Where is the rectifier? So I think we should try and open it a lot more. Oh, just removed the fan. Oh, look at that. Now I can see it's full of corrosion and also some nasty stuff. And yeah, this is one of the 3 that I've just been testing. I think it's about half an hour, 45 minutes ago since I tested this one. So I'm not super afraid to touch it, but I don't go and stick my fingers on anything because you can see the size of those capacitors, so they could potentially be a little bit nasty to touch. But yeah, we got quite a lot of big transistors in there. It was not that difficult to take it out of the case, but you can see we got some holes like that one. Access to the screw, and here is a screw. So you have to, and that one is again. So it's, of course it is made so you can access the different screws. That one down there was a little bit difficult to access because some of parts of the transformer was a little bit in the way. And down here we got some screws as well, right? But anyway, it's out of the box and we can have a little look. Yeah, this is mains entry, that connector here, right? So what I've done is I put on 10 volts DC, exactly 10.0, and then I simply just followed the tracks and the system around this. So you got some capacitors, you got the first common mode filter inductor here, then you got some capacitors and a second filter, common mode filter of course, and we got some more capacitors, and here we got some resistors for measuring the mains voltage so that everything is now in perfect phase and control with input sine wave, because this is mains AC input. And as you can imagine, this one is a bridge-less boost converter. So there isn't any rectifier bridge in the beginning of this circuit. And there is a reason for that, because that stuff generates voltage drop and power loss. And here we got the two PFC inductors. They are of course connected. Each of them is connected to each side of the AC input. I don't know if that is super easy to see here. And then this the two ends of the two inductors here, they just go down here. And here we go. I have marked with black permanent marker. Two field effect transistors and two diodes. And what you see here is one of the large capacitors and the other one here. Those two capacitors, they're just in parallel. And on the two negative sides of the two capacitors, we got sense resistors for current. And then you got the source of the field effect transistor on each side. And one drain goes to one side of each inductor. Okay? And one side of each drain goes to one of the diodes and then to the capacitors. I think it's probably possible to see what I'm talking about here as well. Yeah, so that is how the PFC and the primary side is kind of made. Let me put this down. So I made a little paper cat here for you guys to see the primary side schematic. So this is the AC, exactly as I said. Filter capacitors, common mode, and capacitors, common mode capacitors. And then we've got the two mega large inductors. And of course, all this is running in interleaved mode. So they're not on at the same time. They go on like that at a high frequency. And that is how you charge your capacitor. Capacitors, we got two of these in parallel, and that will be the two sense resistors. So that is how our PFC works. And of course, since this boosts the voltage up to a higher voltage, the current is less, and that means you will have less power loss here. If you put a bridge rectifier on the AC, just like most switch mode converters are made, and then you have the PFC on the DC bus, and this is, I mean, 99% of all switch modes, they are made like that. But then you will have, at a relatively lower voltage, much higher current through your bridge, and you'll have two of them always conducting. And you can imagine here, we have less than half of that, because we only have one of them at a time, and you only have one because the other one is the FET. That is more or less zero loss, right? But then again, much higher voltage, and then again, less current means less loss. So this is a very, very effective way to boost and PFC and rectify at the same time in one go. We can now look at the rest of the converter system here. So from the two main capacitors, we got two field effect transistors down there. We can just barely see the screws. I don't know if that is possible to see, but anyway, that is a half bridge push-pull, and then you go through an inductor and to the primary side of the transformer. And I believe that is because they're creating a resonant primer system where they need more inductance than was available in the transformer. So that is why they added another inductor here on the primary side. There's actually also another thing that I think what they're doing, and that is because normally you see the diodes on the secondary side. Here they are 2 and 2 field effect transistors, so it's a synchronous active rectifier. So again, they can rectify without loss or with very, very low loss. But normally you have an inductor on the output side to smooth out the current and to make it a sawtooth current. But you can of course also put that inductor on the primary side where the current is much less, and then use the transformer to transfer this inductance. So I think this is a pretty smart way to do it, to make this inductor half the size. Normally it will be at least the same size as the transformer, but now it can be half the size because it is on the primary side. That is so smart what they're doing. And here you got the 4 transistors, 2 and 2 in parallel, and that will be individual gate drivers. They're running in sync for the FETs. And of course you need individual gate drivers. You can't just parallel field effect transistors. You will have a coupling from the drain to the gates on each of them, and that will cause all sorts of problems. And this is exactly why they have individual gate drivers here, so they got everything under control here. The very, very high peak currents that's running in this rectifier, they need somewhere to handle that. And they can only do this by ceramic capacitors, because they got very, very low internal resistance, and low loss here is super important. So all these capacitors here, yes, they handle 42 amps of high frequency current. And then we are down in slow speed current, and then we can go into capacitors here, and they aren't really for AC anymore. This is just a DC output now. So that is why it's possible to go down in just these 3 little capacitors, because they can't handle 42 amps of ripple current. Those 3 small ones, they can handle like 5 amps each on a very good day, really. And that will be our output. Yeah, so that is a very, very nice power supply. Or the PCBs here, there are 4 layers. And I kind of like the way that they are interconnected. Look at the way that you stick in one board into the other one and just solder fast, splatty splat, and that way, and then also here, and then you're done. They even made a nice spacing here, so you could easily desolder everything and detach the 2 circuit boards if you wanted to. I wanted to show you one more trick before we leave. I try to focus lock it, but that is not going to work. Down there, can you see the microcontroller and the crystal down there? So everything here is completely microcontroller, controlled, obviously. Okay, it could also be an CPLD or FPGA or something like that, because you really want to do quite a lot of things really, really fast, and you want to have several loops that's doing different things for the PFC, the main switching, the output power. You want to do over voltage, you want to do current. There's a lot of stuff you want to do here. And so that is probably what they're doing there. I can't get in more than that, because then it's going to be a little bit difficult for me to put it back, I guess. Yes, I think I also found the minimum load. I think this one, oh, sorry about that. Here we go. I think this is a power Zener diode and a resistor, and those 2 are in series with the output. So I think what happens is that when there is no load, the voltage just rises to 55 volt, and it will of course pick this up, and it will just load the output with these 2 components, and then it will just stay there. I was able to find the datasheet of this power supply. The funny thing is that they call it a rectifier. That's a little bit funny. They also call it 48 volt DC. And if you look here at the top under the description, they just call it a nominal 48 volt DC. Adjustable, I think that is probably so you order them with to the voltage you need. And the power supplies I got, they have been adjusted for 55 volts. That means the top up voltage of lead acid batteries. If we scroll down a little bit in the manual, we see here on the left side they talk about high efficiency, 96.5%. I think that will be the top score of the curve. So I think I will try and see if I can recreate that scenario. Look at the curve here. This is from 10% to 100% load. And of course 100% load is 2000 watts. So that means the peak of this curve is about 40%. So 40% is 800 watts if I'm not mistaken, right? Later in the manual we see all the figures and all the details, and we also see the top up voltage. So here it is in fact explained that my output is 55 volts, and then you see the amp curve go up to 42 amps or something like that. So that is quite a lot of watts. Yeah, the peak efficiency is explained here. Yeah, exactly 96.5, but unfortunately they don't say at exactly what load current I need to do this at, so I will need to do a little bit of experiments. So I've been sitting and playing a little bit with the efficiency of this power supply, and remember we've been looking at the data sheet, and the efficiency curve tops at about 40% of its maximum potential, and 40% of 2000 watts, that should be around 800 watts. So that is my goal. So I've been trying a little bit more and a little bit less of about 800 to 900 watts of output to see where is the maximum efficiency. So this is 4 amps per load, and I got all the loads connected to the output like this, and since it's only 4 amps I can just use my little grippers for that. And this is my input power, and this power meter does indeed measure the correct power and everything in correct phase relation and all that, so it is definitely correct. So that was my 30 watts of idle, and then I can just crank on a load at a time. So that is 218 watts output, and then we got 245 input, and the next one is another 218. So then we have 468 on the input side, and then we just crank on one more, another 200, and this time it's 219. And this is the correct power, by the way, because this one is using a Kelvin lead and a Kelvin grippers. So this one got sense wires all the way down to that point. So this is the correct power, since current is correct on all of them. Now I got 3 times 219, and then it is 694 on the input. And then we just take now 4 times 219, and the input power is now 923 watts. So that is an efficiency of 95.9%. Isn't that just amazing? It didn't even crank up the fan. I couldn't help it going out and picking up another one, and so I'm comparing if they got exactly the same efficiency. So this one had 95.9 as the highest possible combination, and that was at 4 amp load. And listen to the fan in this unit. It's nice and quiet. It's using about 30 watts of idle. And now I'm cranking on the 4 amp, 4 amp, 4 amp, 4 amp. So this is a total of 872 watts. at the moment. That is my load. And here is a 910 watts of input. So that is 95.6% efficiency. But the funny thing is, now the fan is not going fast. Then I turn off the loads. And then when I tried to do this before, then the fan went berserkers. So there's probably a temperature delay on where it's measuring the temperature and then controlling the fan. But it can definitely control the fan. I just don't know how long time it takes yet. But anyway, I don't want to say a lot more about these power supplies. I think you have already seen what there is to say about it. Thank you very much for watching, and please come back again soon. Bye bye.